Homework 1.4, section complex numbers. Video number 2, homework due May 16th, 2020. Types of numbers, part 2. The previous video had already passed the 10-minute mark, and although that's okay, I've still got quite a bit to say, so I went ahead and stopped after the development of the rational numbers. If you haven't watched video 1, you might want to go back and check it out. I'll summarize it real quick. We're looking at the historical development of sets of numbers, starting with the counting numbers, which are the numbers you count with. Next one is the whole numbers, which is the counting numbers with the addition of 0. And then the integers, which are the positive and negative whole numbers and 0. And then the last one we talked about were the rational numbers, which are more commonly known as fractions, called rational numbers because they are ratios of integers. So basically, you build things that look like this by putting one of these numbers on top of another, as long as the bottom number is not 0. Now, it's important to point out that as we move from set to set, we're not going to a different set, we're just adding more to the one that we previously had. For example, when we went to the whole numbers, it included all the counting numbers. When we went to the integers, it included all the whole numbers. And when we go to the rational numbers, it still includes all the integers. Why? Aren't rational numbers things that look like fractions? Yes, but every one of these integers can be viewed as a fraction. How can you turn something that's not a fraction into a fraction? By putting it over 1. And these aren't the only fractions that I could create. For example, to get 3, I could put 3 over 1, or 6 over 2, or 300 over 100. So there's actually an infinite number of ways to generate each integer as a fraction, but the most common way is to just put it over 1. So again, when we transition from one set of numbers to another, we're not sidestepping and picking up different types of numbers, we're adding to the numbers that we already have. So from integers to rational numbers, we pick up all the fractions, all the fractions, all the ratios of one integer over another. And you might think that's all of them. In other words, you might think if you draw a number line, every dot on there, on a number line, is a rational number, is a ratio of integers. But actually it's not. Because there's another way to describe the rational numbers. Without getting into the arithmetic side of things, when you have a fraction, you can turn it into a decimal by doing the top divided by the bottom. And if you do one integer divided by another, one of two things will always happen in terms of the decimal. Either it will stop, such as 1/2 equals 0.5, or 3/8 is equal to 0.375, or it will repeat, such as 2/3 equals 0.6 repeating, or let's do 7/11 equals 0.63 repeating, if you trust me. But every rational number as a decimal will either terminate or repeat. So another way to describe the rationals, not in terms of fractions, but in terms of decimals, are all decimals that either terminate, so they stop, or repeat. And there are some old school thoughts that say all rational numbers are repeating decimals, because if it ends, you could just stick a 0 on it with a repeating bar over it and say, see, it's got a repeating 0. Nobody ever does that anymore. So we can think of rational numbers as ratios of integers, but we can think of them in terms of decimals that either end or repeat. So why am I bringing this up? Well, remember the game that we played in the previous video where we tried to create an equation using the numbers that we had, whose solution was not in there, and necessitated the need to create another set of numbers, a larger set of numbers? Well, the same thing with the rational numbers. But I can't create an equation using rational numbers that doesn't have a solution if I limit myself to addition, subtraction, multiplication, or division. So how can I create an equation in rational numbers that doesn't have a solution that's a rational number? Exponents. For example, consider the equation x squared is equal to 2. Now, I mentioned in the previous video that there are certain skills I expect you to already have. This one may or may not be one of them. Do you know what to do to both sides of this equation to solve it? In other words, to get the x by itself. Now, this is something that we are going to go into much detail in the next series of videos, But to get rid of a square in an equation, you can square root both sides. I'm going to put a plus minus. Actually, before I do that, let's back up for a second. Let's say I asked you to solve x squared equals 9, which is made up of rational numbers. Remember, every integer is a rational number. If we square root both sides, it cancels the square. The square root of 9 is 3 because 3 squared, or 3 times 3 is 9. But this equation actually has two solutions, 3 and negative 3. 3 times 3 is 9, but negative 3 times negative 3 is also 9. So when you use a plus minus, again, we'll talk about that in the next series of videos. Right now, the important thing is that we can square root 9, get 3, and that's a rational number because it's an integer, so it's a rational number by default. But what if we had something like x squared equals 2, and we did the same thing? Square root both sides. I'll bring in the plus minus on the next line. What's the square root of 2? In other words, what number can you multiply by itself to get 2? If you've got a calculator and press the square root button on the 2, it will tell you something that's approximately 1.414. But notice I said approximately. As a decimal, the square root of 2 does not terminate and it does not repeat. My face might be off the screen. I forgot how far to the side I'm going. So we run into a problem with the square root of 2. As a decimal, it doesn't end and it doesn't repeat, which means it is not a rational number. In fact, a decimal that does not end and does not repeat is called an irrational number, chosen specifically to mean the opposite of rational. Now, is that the next set of numbers, irrational numbers? No, because in this progression, we're not going to the side and picking up different numbers. We're taking the numbers we already have and adding more to them to get a bigger set of numbers. So in order to get from the rational numbers to the next set of numbers, we need to pick up what's missing, and what's missing are the irrational numbers. So when we take all the decimals that neither end nor repeat and throw them in with the rational numbers, in other words, when we get all the irrational numbers and combine them with the rational numbers, we get what are called the real numbers. Now there's two ways to describe the real numbers. You can either say it's the union, so we're joining together, of rationals and irrationals. You'll have to forgive me, I'm taking the adjectives rational and irrational and turning them into nouns. Rationals meaning rational numbers, irrationals meaning irrational numbers, any decimal that never ends and never repeats, like the square root of 2 or pi. But there's another way to think of the real numbers. Well, the rationals are all decimals that either end or repeat. The irrationals are decimals that neither end nor repeat. So together, the real numbers are just all possible decimals, regardless of whether they terminate or whether they repeat. Now, the strict definition of real numbers is beyond the scope of this course. You would have to take a class called Real Analysis, but trust me, we're not going to go anywhere near that. All right, so let's recap what's happened in the development of numbers. We started counting, we picked up 0, we picked up negatives, we picked up all the fractions, aka the decimals that are predictable. They either terminate or repeat. And then we picked up all the other decimals that don't. And we get the real numbers, which are all the numbers on the number line. And for the longest time, that was it. That was it. We're done. We don't have any more numbers. But theoretical mathematicians, God bless them, and I'm one of them, love to push the envelope. Can I make an equation with real numbers that doesn't have a solution that's a real number? The answer is yes, and it goes back to squaring. What can you square to get -1? Ponder that for a second. Something times itself is equal to -1. Do you see the problem with that? Something times itself is -1. Well, assuming you know the rules for multiplying, and you should, when you take a positive number, let's get out of number line because we're currently living in the real numbers. All the numbers on this number line. So the negative numbers back here to the left, the positive numbers back there to the right, and of course 0. Typically written in the middle, but nobody said you had to look at 0. You could look anywhere else. Good luck finding a solution to this on this number line. Because if you take a positive number and multiply it times itself, it's positive. But what happens if you take a negative number and multiply it times itself? Well, negative times negative is positive, so that wouldn't be a solution either. I'm trying to get negative 1. The only number left is 0, and of course 0 squared is not negative 1, it's 0. So it looks like they reached the end of the road. We found an equation that we can't solve. Because no number on the number line, when you square it, will give you negative anything, much less negative 1. And it stayed that way for a long time, for centuries. And finally, recently, and when I say recently, in terms of the history of math, I mean about 400 years ago, somebody said, you know what? Why did we stop? Why can't we just do something to move it forward? We made up 0, we made up negatives, we made up rational numbers, and hey, there's other irrational numbers, and is that the end of it? I can't remember who to blame for this, but it's probably a French mathematician. You can blame them for most of the things that people don't like in math, for graphing, for logarithms, and probably for what's about to happen next. But somebody said, why can't we finish this? I mean, we know how to solve it up here. Why can't we do the same thing here? Why can't we just square root both sides? Get a plus minus, which we'll talk about later. So really the root of the problem, pun intended, is what to do with this thing. What's the square root of negative 1? And it just simmered and stewed and festered for the longest time. And finally somebody said, look, I'm just going to make up a definition. We don't know an answer to this, we'll make up an answer for it. And this is where people's eyes usually start rolling into the back of their heads. What do you mean, make up an answer for it? Well, believe it or not, based on what I'm about to write, we get things like wireless technology, so you're welcome. Get into electrical engineering if you want more details. Somebody said we're going to give this a definition. We're going to call the square root of negative 1 I. Now, don't ask me what I equals, I'll tell you the square root of negative 1. And don't ask me, well, what's the square root of negative 1? I'll tell you I. And if you ask me why, I'll say because it's a definition. This is the symbol for the answer to this problem. Now, it's important to point out that it's not a real number. We've already said that no real number will make this equation true. X squared is equal to negative 1. So why do you think they chose the letter I? I'll give you a hint. They needed a word that meant not real. And that word was actually imaginary. This is the definition of an imaginary number. It doesn't mean it doesn't exist. It just means it's not real, aka on the real number line. But I'm going to have a real hard time showing you this number visually. I can show you 5. I can show you a half if you give me an apple and a knife. I can show you negative numbers if I write a check that's bigger than my bank account and it clears. But I can't show you $. So what is this definition really saying? What it's really saying is if you see the square root of negative 1, change it to I. Change it to I. And what are the consequences of this command, if you will? If you see the square root of negative 1, change it to I. Well, the consequences are we get a whole new set of numbers. I'm just checking the time on the video. Oh, this one went even longer than the previous one. All right, so I'm going to go ahead and wrap up this video. The next one's not going to be types of numbers part 2, but we're going to get right into imaginary numbers and complex numbers. But keep this in mind. This in the cloud is one of 2 key moves you need to know for this section. If you see the square root of negative 1, you change it to the number I. In the next video, we'll talk about the types of numbers this creates and how to do arithmetic with them. Again, keep in mind, if you see the square root of negative 1, change it to I, because you're about to see it a lot.